Data for everyone. All right, okay, all right. Okay, so this is the next topic that we're doing, normal distribution. So in the last topic, we talked about discrete variables and continuous variables, binomial and geometric distributions. Both of them were discrete distributions, right? The variable could only take integer values in that case. But now, normal distribution is a continuous distribution. The variable that you would have in this case, it can take any real value, right? So any decimal values are also going to be possible in this case. Now, for normal distribution, this is the first thing that you need to know about. It's a continuous distribution, and it's described by its mean and variance. For describing a normal distribution, you need two things. Number one, the mean, and number two, the variance. Okay. Now, this is the notation that is used here. For mean, we use mu. For variance, we use sigma square. If you have something written like this, x and then tilde, and then you have n, 15, 25. What does this represent? Inside the brackets, the first number would represent the mean, and the second number would represent the variance. Okay, so this notation, n, 15, 25, what that means is x follows normal distribution with mean equal to 15 and variance equal to 25. Now, in this notation, this number represents variance. That's very important to remember. But in our calculations, as you will see, we will be using standard deviation. So standard deviation is square root of variance. If variance is 25, standard deviation is going to be 5. You just take square root of that, and you get the standard deviation from that. Okay. Now, we will be using this normal distribution curve to find probabilities. Now, again, the idea is we will have some situation given, and we would have to find some probabilities using that. In geometric and binomial, we had some formulas that we used to use to find probabilities. In this case, we will be using area under a curve to find probabilities. Okay. Now, this is what the normal distribution curve looks like. It's also called the bell curve. It's a symmetric curve. The area under this curve represents probability. Area under this curve represents probability. Now, the total area is going to be 1, of course, because total probability is 1. It's a symmetric curve, so if you break it in the middle like this, the area on the right side and the area on the left side, they're both 0.5. And in the middle, you have the mean of the distribution. Okay, so the distribution is symmetric about the mean. So when it's perfectly normal, yes, mean and median are going to be the same in this case, if it's a perfectly normal distribution. As you go close to the mean, the probabilities are bigger. So you have more area under the curve close to the mean. As you go far away from the mean, the probabilities become smaller because there's less area under the graph. Okay, and in the middle, there's more area under the graph. As you go far, there's less area under the graph. Now, how do you find this area under the graph? Actually, this area is found using integration, as in the logic behind that is this integration is quite complicated. So what we have in the exam is that they give us a table that we will be using to find these areas. Okay, we'll talk about how to use that table, but the idea would be, let's say you've got a variable like this. It's a variable x. It represents test scores of some students. Okay, so remember, it's supposed to be a continuous variable. So you can have any decimal value in this case as well. If it's a normal distribution, any decimal values are also possible. Now, in this case, let's suppose we have this data about a test in a class. The mean of the whole class is 60, and the standard deviation is, let's say, 12. Okay. Now, if we had to find the probability, for instance, that somebody got a test score of less than 60. Now, 60 was the mean. So 60 would be exactly in the middle of this normal distribution curve. So less than 60, what would that area be? That would be 0.5. Okay. However, if it was something else, for example, x less than 70, we could say this number is 70. We're looking for all of this area towards the left of 70. Now, that is something that we can't really, find directly like this. There will be a process that we use for this. We'll talk about that. how to find, for example, probability of x less than 70. We'll talk about that in a minute. But in normal distribution, you need to understand less than something or less than equal to something, they're both the same thing. Greater than or greater than equal to something, they're both the same thing. Equal to does not make any difference. Equal to does not make any difference in normal distribution. In discrete distributions like binomial and geometric, these two would have different meanings. In normal distribution, they're both the same. Why? Because probability of the variable being equal to any particular value is actually 0. Because if you find the probability of x equals, let's say 65 or 40, where will 40 be? 40 will be somewhere here on the left side. Let's say this is the point 40. Now, probabilities area under the graph, this is just a point. What's the area under a point? There's no area under a point. Under a point, there's just one line. There's no area there, right? Another way to think about this is in continuous distribution, since the value can be any decimal value, when you say something like this, probability of x equals 40, what it actually means is somebody has a score that's exactly like this, 40.00000. Now, in test scores, it might not make a lot of sense, but think of some other variable, for example, height of a person. So what's the probability of somebody having a height that is exactly, let's say, 5.5 feet? So exactly 5.5 feet means it should be 5.500000000, and then infinitely many zeros like this. It's very unlikely that somebody has a height that's exactly 5.5 to the dot, and there's no even a 1 after a billion decimal places. It's very unlikely, right? So in this case, we say probability of something being exactly equal to some value in normal distribution, that's going to be 0. So we would not generally be finding probabilities at a particular point. We will always be finding probabilities for an interval in this case, right? So less than something, greater than something, between two values. We will not be talking about these probabilities because they will be equal to each other. But why are they important? Because you need to understand that these two are the same thing. They don't have any difference. Now, how do you find this probability? Probability that x is less than 70, for instance. How do you use this curve to find this area? Let's understand that. Now, for this, we have something that we call the standard normal distribution, okay, that we will be using to find these areas. Now, finding these areas is, as I said, done using integration, but that integration is pretty complicated. So you have the results from this integration given in the form of a table. Now, before we move on to this, let's go and understand how to read values from a table. So you'll be using a table, and that table represents areas of a normal distribution like this. It's called a standard normal distribution. A standard normal distribution is one in which the mean is 0, variance is 1, and standard deviation is also 1. So there's a standard normal distribution, which we also call Z distribution. It's a distribution such that the mean is 0 and the standard deviation and variance, they're both equal to 1. So what we would do would be, whatever distribution we have, we would be converting that to a standard normal distribution and then use that to find values from the table. Now, how will that work? Let's understand it using this table. Let's understand first of all how to read the table. Okay, so you'll have a table that looks something like this. These highlighted regions that you see, let me just get rid of this quickly first. Okay, so these highlighted row and column that you see, the first column and this first row, they represent Z values. They represent the Z value. Okay. Now, the blue line that you see, the blue column that you see, it represents the unit place and the first decimal place for the Z value, 0.1, 0.0, 0.1, and so on. This yellow part on top, that represents the second decimal place, and the green part here represents the third decimal place. Okay. Now, for example, if there's a Z value of 2.4, where is 2.4? This is 2.4. These values here, the unshaded part, this represents probability. So you'll have a Z value and you would have probability corresponding to that. So let's say there is a Z value of 2.4. How do you find the corresponding probability value from this? This is the Z value. This number that you see, that's the probability. That's 0.9918. Probability corresponding to this would be 0.9918. Okay. And similarly, if you had more decimal places, for example, if you had a Z value of 1.34, let's say, Z value of 1.34, what will be the probability corresponding to that? 1.3 is going to be found in this region. This is 1.3. And then 4, that's here. You would come down here, go to the right here. This is the value that corresponds to that. And the probability value that you get from that is 0.9099. So when you have two decimal places, you can just do it like this. Read the first decimal from here, second from here, and you get the result from that. In your formula sheet, it's not going to be shaded like this. So you need to remember that this first column represents first decimal, this represents second, and the green part represents the third decimal place. Okay, now if you had 3 decimal values in Z, for example, if you had 0.675, what's the corresponding probability value for that? You'll find 0.6 here, you'll find 7 here. That gives you 0.7486, but then there's a third decimal place there as well, and that is 5. That's here. You say add 16. So this says add here, right? Add means 0.7486. That's the value that you get from there. To the last 2 decimal places, add 16. And that will become 0.7502. Now, you can do it mentally, and that's perfectly okay. If you find it difficult to do it mentally, on your calculator, put something like this. Without the decimal, input this on your calculator. 7486 plus 16, and that will give you 7502. And then what you can do is you can just put a decimal in the beginning, and that will be the probability. Okay, so that's how you find probability values using Z values. It could be 1 decimal, 2 decimals, 3 decimals. All right. Now, when you're doing calculations, you will see sometimes you will have Z values that have more decimal places like this, 0.66667. Now, in the table, the Z values are rounded off to 3 decimal places. So before you read the table, you should round them off to 3 decimals and then read the value from the table. Okay, now there's a problem. And the problem is this Z value that you see here, these probabilities that you're given here, they're only given for one specific case. And you can see that in all of these expressions that I wrote here, I wrote Z less than this value, Z less than this value, Z less than this value, right? So the table only gives you probability values for one specific case. And what is that specific case? It's when you have something like this. There's a positive Z value. And you're finding the area to the left side of that. So in all of these cases that you saw here, Z less than a positive value, Z less than a positive value, Z less than a positive value. This is the only form for which the table gives you the area, right? So less than 2.4, less than 1.34, less than 0.675, all of these values are positive, and we're considering area to the left side of them. To be able to use this table, you need a form that looks like this, Z less than a positive value. Okay, this is the only form for which the table can be used. If this is not the form that you have, then the table cannot be used. Okay, so table is only used for this particular form, Z less than a positive number. And it's shown here using this graph as well that you will get in the exam. In the formula sheet, you'll have this graph given, and that tells you that you're looking at the left side of a positive value. Okay, so that's how you read this table. Now, once you understand how to read the table, let's go back there and understand how to find those probabilities. Now, remember that table that you're given, that is only for this one standard distribution where mean is 0 and standard deviation and variance they are 1. Now, you could have many different types of data sets in which the mean could be anything, the standard deviation could be anything. The table is only for one specific case where the mean is 0 and the standard deviation is 1. So what you have to do is, whatever is the data that you're given, for example, in this case, the mean is 60. the mean is 60 and the standard deviation is 12. Whatever data you're given, you would first have to convert that to a standard normal distribution. You'll have to make the mean equal to 0 and you'll have to make the standard deviation equal to 1 somehow. Now, how is that done? That is done using this formula z equals x minus mu over sigma. It's not given in the formula sheet. You need to memorize this. Z equals x minus mu over sigma. What this formula does is, whatever value you give to it, it subtracts mean from that and it divides by the standard deviation. What that does is it converts the mean of the distribution. It converts the mean of the distribution to 0 and standard deviation to 1. So whatever value of x you have, for example, if you have a data like this, these are x values. You convert them to z values. How? By inputting in that formula. For example, if x is 48, you would say z is going to be 48 minus the mean, that's 60, divided by standard deviation, which is 12, and that gives you minus 1. That's the z value that you get corresponding to 48. And similarly, for all of those values, you find the corresponding z values. Okay, so that's how you convert something to z. And now, if you were to find the mean of all of these values, standard deviation of all of these values, you would see, if you had all of these values written down here, the mean would turn out to be 0 and the standard deviation would turn out to be 1. And then we could use that normal distribution table. Now, this is important. We'll talk about this later again as well. Z value, what does it represent? The Z value represents the number of standard deviations a particular value of x is away from the mean. This understanding is very important. It will make some questions later on, as we'll see, much more efficient and much more easier. When they talk about number of standard deviations of values away from the mean, we could use the Z value directly. If we have this understanding of Z value, what does Z value represent? Z represents the number of standard deviations of value of x is above or below the mean. For example, look at this value, 84. Mean was 60. 84 is 2 times the standard deviation above the mean, right? Because standard deviation was 12. So if you add 24 to the mean, you get 84. So the Z value, see, that turns out to be 2 because it is 2 standard deviations above the mean. Similarly, if you look at 48, this is 1 standard deviation below the mean. 60 minus 12, that is 48. So 1 standard deviation below, you can see the Z value that you're getting for this is minus 1. Okay, similarly, another value, for example, you've got 78 here. 78 is 60 plus 1.5 times the standard deviation. So this is 1.5 standard deviations above the mean. The Z value turns out to be 1.5. So these values of Z, they are representing the number of standard deviations you are away from the mean. The number of standard deviations are above or below the mean. If you're above the mean, the Z value would be positive. If you're below the mean, the Z value would be negative. Now, keep that in mind. We'll refer back to this later on when we look at some of the more difficult questions later on. But that's the idea. Okay, so the idea is whatever x values we're given, we convert them to z first of all to find probabilities. Now, how exactly are we going to find those probabilities? Let's consider this example. So we had that data that I showed you earlier. The mean of that data was 60 and the standard deviation of that data was 12. Okay, let's suppose we wanted to find probability of x being less than 60. Probability of x being less than 60. As we saw earlier, we could not do that directly from just looking at the diagram. How do you find this area? Now, to be able to use that table to find the area, what we do is we first of all convert it to z. How do we do that? Using that formula, z equals x minus mu over sigma. Okay, whatever value of x we are given, what we do is we convert that to z first of all. So 70 minus the mean divided by standard deviation. And that gives us the corresponding z value. In this case, that turns out to be 0.833. So the original distribution looked like this, with 60 as the mean, and we had to find the area to the left of 70. What we do is we convert that to the z distribution such that the mean is 0, and we say in the x distribution, this area to the left of 70, that corresponds to the area to the left of 0.833 in the z distribution. Okay. So what we do is we find the corresponding z value from that. And now this is something that we can find from the table. You have to make sure that you round this to 3 decimal places, first of all, before you can read the table. And now this is z less than 0.833. This is the standard form. We can go to the table, read that value of z, read the probability value corresponding to this value of z, and that will turn out to be 0.7975. And that's the final probability that we were looking for here. Okay. Now, this was the standard case. This was the standard case where you had z less than a positive number. But a lot of times you would not have that. For the table, we need this form z less than a positive number. Otherwise, we cannot use the table. What if it was some other form? For example, if you had to find probability of x greater than 90, same data, mean 60, standard deviation 12, you would convert it to z first of all. So it becomes 90 minus 60 divided by 12. And that gives you that z is greater than 2.5. Z is greater than 2.5. Now, that's not the standard form. The standard form is z less than a positive number. That's the only form for which we can use the table. Now, how do we think about this? We can draw a normal distribution curve. We can say, okay, z is greater than 2.5. What does that mean? 0 is going to be in the middle. 2.5 is on the right side. We want this yellow region to the right of 2.5. That's the area that we're looking for. That's the area that we're looking for to the right of 2.5 there. Right? That's the area that we want. However, the table cannot give us that area. The table cannot give us area to the right of some value. It can only give us area to the left side of a positive value. So what we do is we say, okay, the total area under the curve is 1. If we subtract from 1 the area to the left of this value, isn't that going to be the same? So total is 1. We can subtract from 1 all of this region on the left side. And that will give us that yellow region. So we could write that probability like this. We could say z greater than 2.5 is the same thing as saying 1 minus probability of z less than 2.5. Okay. And now this is the standard form. We can use the table for this. Go to the table, find the probability value corresponding to 2.5, and that will give you the result. 1 minus that, that's the final probability that you get from this. Okay. Now, similarly, you'll have a number of different cases that you could have for finding probability here. So we started with x less than a positive value, z less than a positive value. This is z greater than a positive value. We convert it to this form, 1 minus that. Okay. But then there are a number of other cases that you will have to think about using the same normal distribution curve. Let's quickly go through those cases. Another possibility could be that you're finding probability of x greater than 54. Now, if you convert that to z, that ends up giving you z greater than a negative value. Z greater than a negative value. So that's z greater than minus 0.5. If you look at a normal distribution curve, 0 is in the middle. Greater than minus 0.5, what that means is you're considering the region to the right of minus 0.5. Now, is that the standard form? Is that the standard form? It's not the standard form, right? The standard form is z less than a positive number. So when we have negative numbers like this, what we generally do in single-sided intervals and one-sided intervals like this is that we flip our diagram. Flip the diagram, what does that mean? Reflect this about the center, about the mean, so that it becomes something like this. So you reflect that and you get this lower diagram. So the area to the right of minus 0.5, that's the same thing as saying, if you flip the diagram, the area to the left of 0.5, so you flip it like this. So you can say, okay, this area, z greater than minus 0.5 is the same thing as probability of z less than 0.5. And now that is the standard form. That's something that you can use the table for. You'll go to the table, find the probability value corresponding to 0.5, and that will give you the result. Okay. So when you have negative values like this, you can flip your diagram. What about this? Z less than a positive number, that's the standard form that we want. What if we end up getting z less than minus 0.65? Again, that's not the standard form. It's z less than a negative number. We cannot use the table for this. So what do? We say, okay, area to the left of minus 0.65. That's what we're looking for. Now that's on the left side. It's a negative value. The first thing we do is we flip this. Okay, we flip this and we say that area is the same thing as this area. Area to the right of 0.65, right? This yellow region, that will be the same as well using the symmetry of the curve. So that's the first step that we could do. We could say, let's convert it to this form. That's the same thing as z greater than 0.65. Do not think of this in terms of inequalities that we're multiplying the inequality by a negative number and the inequality sign reverses. No, that's not what we are doing here. In that case, the z would also become negative, right? we're not thinking about inequalities here. Do not think of it that way. Always think of the graph. Think of the graph. Think about the area under the graph. The area under the graph here is the same as the area under the graph here. So that's why we can write this form like this. So z greater than 0.65. But now it's still not the standard form. So what we can do now is we can say, okay, the total area is 1. Subtract from 1 the area to the left of 0.65, and that will give us that yellow region, and that is something that we can find from the table now. Z less than 0.65. We can find this number from the table, subtract that from 1, and that gives us the probability. Okay, so that's what we do for one-sided intervals. For negative values, we flip them first, and then we do that calculation. Sometimes you'll have intervals like this. So for example, z could be between 1.3 and 2.1, let's say. Now, in this case, how do you find this area? Between 1.3 and 2.1, what that means is you've got 1.3 value and 2.1. Both of them are positive values. Both of them will be on the right side of the normal distribution curve, right side of the mean. You've got 1.3 here, you've got 2.1 here. We want z to be between these values. So we're looking for this shaded region. This is the area that we're looking for. How can we find that? Remember, the standard form is z less than a positive number. That's the form for which we can use the table. So what we do is we say, let's find the area to the left of 2.1. Area to the left of 2.1, all of this area. Okay, subtract from that area to the left of 1.3. And that would leave you with the shaded region that you've got here. So that's what we can do. We can say, this area, again, do not think of inequalities. Do not think of inequalities. We're thinking of the area on the graph. On the graph, the area to the left side of 2.1, if you subtract from that area to the left of 1.3, you will get this area in the middle. Okay. And now both of these are standard forms. Z less than 2.1, you can find this from the table. Z less than 1.3, you can find this from the table. Find those two probabilities, find their difference, and you get the result. What if you have negative values in the interval? So if you have minus 1.5 and minus 0.3, if both of them are negative, what we do is, no, we don't have to subtract from one anywhere here. Both of them are positive, right? Z less than a positive number, Z less than a positive number. We don't have to subtract anything from one. These are both standard forms. We just find them directly from the table. These are direct values from the table. We are not subtracting anything from one here. Okay, let's have a look at this. Z is between minus 1.5 and minus 0.3. Okay, now these are both negative values. So on the graph, that's this shaded region. That's this shaded region, right? Now, how do you find that? Both of these values are negative. So the first thing that we do is we say, let's flip this. Let's flip this, and that will give us this corresponding area. So between minus 1.5 and minus 0.3, using the symmetry of the graph, we can say that's the same thing as saying Z being between 0.3 and 1.5. And now again, this is the same as the previous case. We've got two positive values. Find the area to the left of 1.5. Subtract from that the area to the left of 0.3. Both of these are standard forms. We can use the table directly from them. Z less than a positive number, Z less than a positive number. Find the probability values from the table, find the difference, and you get the result from that. Okay. Now, the most complicated case is when you have something like this, when one value is negative in that interval and the other is positive, right? So you have this negative value and the other is positive. So Z is between a negative value and a positive value. Now, in this case, the problem is flipping does not help, because even if we were to flip this on the diagram, the thing is one of these values is negative and the other is positive. So if you were to flip this, this would become positive and that will become negative, and we still have one negative number, one positive number. So flipping this right away is not going to help. So how do we think about this? We think of it, this is one way of doing this, that we think of it like this. We say, okay, area between minus 0.9 and 1.2, that's what we're looking for. Let's find the area to the left of 1.2, all of this area. Subtract from that the area to the left of minus 0.9. Okay, just like we used to do in the first case that we saw earlier. For a two-sided interval, we say, let's find the area to the left of 1.2, subtract from that the area to the left of minus 0.9. Okay, now when you split it into two parts like this, this is now the standard form. This is the standard form, Z less than a positive number. You can find this directly from the table. There's no problem with that. The problem is this one. This is not standard form. So you have to convert this part to the standard form now. How can you do that? We've done this case before. Z less than a negative number. You can think of it like this here. We're talking about this area. That's the area that we're looking to find. First of all, we could flip this, and that becomes the same thing as the area on the right side, right? That becomes the same as probability of z greater than 0.9. It becomes that, right? And then you can say subtract from 1 the area to the left of 0.9. And that gives you this 1 minus probability of z less than 0.9. That is what is going to give you this particular area. And now you see, we have converted this to standard form as well. This is standard form. This is standard form. This is also standard form. We can find these directly from the table now. Find these two values from the table, input them here, and that is going to give you the result. After simplification, you get that area. Okay. So that's what happens when you have one negative value and the other positive value. So that's the case in which you have simple normal distribution. Simple normal distribution means when you have some data given and you have to find some missing, you have to find the probability from that, right? You've got data given, you have to find corresponding probability value from that. That's how we work with this. But then there's another case, and that is when you have inverse normal. You would have inverse normal. Inverse normal, what's that? Inverse normal is when you have some information given about probability and there's something missing in the data. In the original data, there's something that is missing. Okay, so you have information about probability value, but mean might be missing, standard deviation might be missing, variance might be missing, and you would have to find that missing information. Okay, you have to find that missing information. Now, how do you do that? Let's consider this example. So let's say we've got a normal distribution like this, such that the mean is mu and the variance is 9. Mean is mu and the variance is 9. Okay, that's what we're given. So if variance is 9, this remember the second number represents the variance, but in our calculation, we have to use standard deviation. So we can find square root of that. Standard deviation is 3 for this. And we're also given that probability of x less than 20, that is 0.6341. Given this information, what we're looking for is, we're looking for the value for mean. We want to find the value for mean somehow. Now, you have the probability given, and you have some missing information in the data, the mean is missing. So this is called inverse normal, where from the probability, using the probability, you have to find some missing information in the original data. Now, how does this work? For this, we first need to understand how to read the table in the reverse direction now. In the opposite direction, how do you read the table? Again, let's go back to the table. This is the table that we had. So now you would have some probability value. So when you have probability value, you have to search in this region. This is the region that represents probabilities. Okay, so you have to search in this region, not in the first column, in the first row. That's z values. You have to do the other way around now. Let's say you are given that there's a probability value 0.8790. So z less than some value is 0.8790. Now, what's that z value? How do you find that z value? That's the question. The z value, how do you find that? You would search for this probability in the table 8790. So the probability values are given in an ascending order from top left to bottom right. So they increase like this in this order. So it's not going to be difficult to find that. They're sorted like this. So 0.8790. Let's search for that value. 0.8790. You keep going to the right. 8790, 8790. This is the value. 8790. Okay. Now this is the value 8790. Corresponding to this, what's the z value? It's 1.1 here and 7 here. You say the z value is 1.17. Okay, and you write that there. So that's how you read the table in the reverse direction. You have the probability given, and you have to find the z value. Now, in this case, in the first example, we could find that exact value in the table. Okay, we could find that exact value from the table directly. Now, what if we had 0.8599? 0.8599. Let's search for this. 8599. 8599. Okay, so this is 8599. Again, what's the Z value corresponding to this? 1.0 and 8, 1.08. That's the Z value that we get from this, 1.08. Let's take another example. Let's say we had 0.8753, 0.8753. Let's search for that. 8753. This is 8749. This is 8770. 8753 is not there in the table. 8753 is not there in the table, right? In the previous two examples, we were able to find that exact value. Now this is not there in the table. How do you find this corresponding Z value for this? What you do is you consider the Z value, the probability value in the table that's immediately smaller than this, 8753. What's the closest value that's less than this? That's 0.8749. You select this from here. Select this from here. The Z value corresponding to that is 1.15, right? 1.15, that's what you write down here. Write down here 1.15 first of all. But then you had 8753 there. In the table, you found 8749. What's the difference between them? 4. So that means you still need to add 4 more to this probability to get to the actual result. This is 4. And that gives you the corresponding third decimal place of Z. That's 2. So the Z value turns out to be 1.152 from this. That's the final Z value that we've got. Okay, let's take another example. So in this case, we had to have the third decimal place as well, and that's how you can find that. Okay, now what about another example? Let's say we've got probability of 0.7080. Okay, 0.7080, let's search for that. 7080, we don't have that here. This is the immediately smaller value that we find, 7054. Now, corresponding to that, we've got 0.5 here, 4 here. The Z value is 0.54 from that. But then we have found 7054. What's the difference between 7054 and 7080? We have 26. So we have to go to the right side now and search for 26 here. Well, do we have 26 here on the right side? We don't in this case. 26 is going to be somewhere here in the middle of 24 and 27. Now, is 26 closer to 27 or 24? It's closer to 27. So we use 27 from here and we say that the third decimal place is going to be 8. And it becomes 0.548 from that. That's the Z value that we get from that. Okay, take another example. Let's say you had 0.5892 and you had to find the corresponding Z value for this. 5892. Let's search for that. 5892. Can we find that here anywhere? 5892. The immediately smaller value is this. 5871. Consider the Z value corresponding to that, 0.22. That's the first two decimal places. But then how much more do you have to add? 92 and 71, the difference is 21. So you need 21 more. You go to the right side and find 21. Now, where is 21? Well, it's going to be in the middle of 19 and 23. We don't have 21 exactly. It's between 19 and 23. So now we think about which value is it closer to. Is it closer to 19 or is it closer to 23? Well, it turns out it's exactly in the middle. It's exactly in the middle. So what do we do in this case now? We either choose this or this. You can choose any of them, and that's all right. You can choose 19 or 23. So the third decimal place could either be 5 or it could be 6. Any of them would work in this case because it's exactly in the middle. So we can use any of those values. So you could say it's 225 or 226. Both of them will be acceptable in this case. All right. Okay. Sometimes the probability value, if you look at the table, all the probability values here, they're given to 4 decimal places. Z values are given to 3 decimal places. Probability values are given as 4 decimal places. If you have a probability that is not given to 4 decimal places, for example, if you have 0.8, you would think of it as 0.8000. Okay, and then search for that in the table. 0.800 is not there. We've got 7995. Z value corresponding to that is 0.8 and 0.4. So that's 0.84. We have to add 5 more to that, and that gives us 2 as the third decimal place. It becomes 842. Okay, now if you had 0.7191, okay, so let's consider that. If the probability value was 0.7191. Let's search for that. Do we have that here? 7191. 7191. Okay. 7190. This is the closest value that's smaller than that. The Z value corresponding to that turns out to be 0.5 and 8. So Z is 0.58, but then we need to add one more to it. Let's go to the right side. Where is 1 going to be? 1 is here, right? 1 is here. Now, is 1 close to 3 or is it close to 0? 1 is close to 0. So in this case, you do not add 1 here because 1 is actually close to 0. So you don't have to. So one choice is that you add nothing, you add 0. And the other is that you add 3. 1 is closer to 0 here. 1 is closer to 0. So you add nothing with that. You say this is 0.580. Okay, so this is 580 or just 58. Now, some values, you would find that some values are given directly at the bottom of the table as well. Okay, let me just show that to you quickly if I can find that. You would find that at the bottom of the table, there are some values that are given to you directly. And these are very common values. So sometimes have a probability of 0.75, 0.9, 0.95, 0.975, 0.99. If we have one of these probability values, you can write the Z value corresponding to that directly from this table at the bottom. These are some common values. You don't have to, you can find these values from the table as well if you want. That will work as well. But you can just look at this bottom table for these common probability values. For example, if for probability is 0.75, the Z value is 0.674. For 0.9, it's 1.282. For 0.9 in particular, from the table, you get 1.281 or 1.282 because the third decimal place, for the third decimal, we'll have it exactly in the middle. So it's either this or this. But in the marking schemes, they normally use 1.282 for this. Why? Because it's already given here at the bottom. So you should prefer using 1.282 in this case and not 1.281. So for common values, I would recommend that you use these values at the bottom and skip the table. You'll get the same values from the table as well, but this is much quicker. That's what you should be using. Okay, let's move on now. Z values are written to 3 decimal places and probabilities to 4 decimal places in this table. Now, let's go back from where we switched to that table earlier. So now we know how to read the table in the reverse order, how to read the table in the inverse order, right? So now let's say we are given that there's a variable such that its mean is unknown. We have to find that, and its standard deviation is 3. And we're given that the probability of X is less than 20, that is equal to 0.6341. How do you find the value from mean? Remember, the table can only be used for that particular form where probability of Z is less than a positive number. So how do you go about finding this value for mean? First of all, you say, okay, if probability of X is less than 20, if that is equal to 0.6341, you think of it like this. Okay, what's the corresponding Z value for this? What's the corresponding Z value for this going to be? So you write it like this: Z less than some expression that is equal to this. Okay. So first of all, you write it like this. You replace X with Z and you say Z less than some value that is going to be equal to this probability. So we have to find the value of Z that corresponds to 20 here. We have to find that value for Z. Now, how do you find that? You cannot use the table unless you know for sure that this is the standard form, because this number could be negative, it could be positive. So the first thing that you have to do always is figure out whether this number here is positive or negative so that you know if you can use the table for that or not. How do you figure this out? You think about the normal distribution curve for this. And that's how you figure this out. You say, probability of Z less than this number, that is equal to 0.6341. So on the normal distribution curve, what we're saying is the area towards the left side. So less than means we are saying area towards the left of this z value that is equal to 0.6341. Now, is 0.6341 a small area or a big area? Remember, the total area is 1. So with respect to 1, half of 1 is 0.5, right? So 0.6341 is more than half. It's bigger than 0.5. So we want the area to the left of the z value to be a bigger value, to be a big value. Now, where do we place z on this normal distribution curve then? Do we place that on the left side, on the negative side, or on the positive side? If you were to place that on the negative side, the area to the left side would be smaller. If we place that on the positive side, the area on the left side would be bigger, and that is what we want. So that tells us that the z value is supposed to be positive here. Now, if that's positive, now we know it is the standard form, z less than a positive number. We can use the table for this. We go to the table, find the z value corresponding to this probability, 0.6341, and that would give you the z value 0.343. Now we've got the z value. We had to find the mean. We use the formula that we've got, z equals x minus mu over sigma. Z value is 0.343, x is 20, mean is unknown, standard deviation is 3. Just input those values in this formula, you get the value for mean from that, and that's what we were looking for. Let's take another example. What if you had something like this? There's a variable x, again, that's normally distributed, and the mean is unknown, variance is 25. Again, we have to find the value for mean. It's not necessary that you'll always have the mean missing. Sometimes you have the standard deviation missing or the value of x missing. It could be any missing information in the data. You have this value of x missing as well. The idea is going to be the same. It's the same process that we follow. If it says probability of x greater than 30 is 0.2. How do we go about doing this? We say that means z greater than some value, this probability is going to be 0.2. And now the first thing we have to do is we have to figure out whether this number here is positive or negative. So again, how do we think about this? We say area towards the right side, area towards the right of this value, area towards right of this value, that is 0.2. Is that a small area or a bigger area? If you compare that with 0.5, that's a small area. So z has to be somewhere such that the area to the right of that is small. So where do we place z then? If we place z on the negative side, area on the right would be bigger. That's not what we want. If we place z on the positive side, area on the right would be smaller, and that's what we want. And now we know that this area here, this is 0.2. But so we understand that z value is supposed to be positive. But the problem is it's not the standard form. It's z greater than something. The standard form for using the table is z less than positive. So we convert it to that form. How do we do that? We say, okay, if the right side is 0.2, then that means area on the left side of this is going to be 0.8. So we can write this as that the probability of z less than that value, that is equal to 0.8. Right? If the area to the right is 0.2, area to the left is going to be 0.8. And now this is the standard form. It's z less than a positive number. We can go to the table, find the z value corresponding to this probability. Right? This probability is 0.8000. Go to the table, find the z value, and that z value turns out to be this 0.842. And that gives you the corresponding mu. When you input that in the formula, you get the value for mean for that. What if you had something like this? Now we've got normal distribution, and we've got the mean of that distribution. We've got the standard deviation and variance. And now they're saying probability that x is greater than some value is equal to 0.725. And we need to find the value for a. We need to find the value of a in this. How can we do that? Again, what's the process? First of all, we write this like this. We say, write this probability in terms of z. X greater than a. Let's say that corresponds to z greater than some value. That probability is 0.725. And again, we think of it like this. We are saying the area towards the right side. The area towards the right of this z value, is that smaller or bigger? That's bigger. So where do we place z then on the normal distribution curve? If we place that on the positive side, area on the right side will be smaller. That's not what we want. So we have to place that on the negative side. So in that case, the area to the right would be bigger. So that tells us that the Z value is actually going to be negative. So Z value is negative here. That's what we understand from that. Okay, so first of all, you have to identify that whether that Z value is positive or negative, and this is telling us that it's supposed to be a negative value. Now, if it is a negative value, that means it's not the standard form. The standard form is Z less than a positive number. This is not the standard form. So what do we do then? We can flip this. We can say, let's flip this. If that area to the right of that negative value is 0.725, if you were to consider the corresponding positive value of Z here, the area to the left of that positive value using the symmetry of the curve, this area should also be the same, right? So if this number was, let's suppose, minus 1.5, the area to the right of that is the same as the area to the left of plus 1.5 because of the symmetry of the curve. So whatever was that negative value, the corresponding positive value for that, the area to the left of that, that will also be 0.725. So what we can do is we can say, we can write this probability as probability of Z less than the positive Z value. That is equal to 0.725. And now this is the standard form. This is something that we can use the table for. Go to the table, find the Z value corresponding to this probability 0.725. And that turns out to be 0.598. And now we don't put this in the formula directly. Since we know that Z value was supposed to be negative, we have to write this as a negative value. So we say the positive Z value, this side, this is 0.598, but the actual Z value was negative. So we put a negative sign with that. And we say this is minus 0.598. Put that in the formula now. You know the mean, you know the standard deviation. X is missing. In place of X, you put A. And that gives you the value for A. You get the result from that. And then the last case for this, when you have a normal distribution that looks like this, its mean is 40, its standard deviation, its variance is 25. And again, what we're given is that probability of X less than B, that is equal to 0.215. And we want to find the value for B somehow. Again, we think of it like this, Z less than some number that is equal to 0.215. And again, that means that area towards the left is smaller. So where should Z be? Z should be on the negative side. That's where Z should be. This is where Z is going to be. It's going to be on the negative side because that will make sure that the area on the left side is smaller. So that means Z is a negative number here. If Z is a negative number, that means it's not the standard form. The standard form is Z less than a positive number. So how do you convert it to standard form then? That's the question. So first of all, we could say, let's flip this. It's a negative number, right? Let's flip this. If this area is 0.215, if we flip this, that means this area here to the right, this should also be 0.215. The area to the right of the positive Z value, that should also be 0.215. But that as well, we cannot find from the table directly. We can only find area to the left side of a positive value. So now we say, if this area is 0.215, then what about the area to the left of this positive value? We could just say that is going to be 1 minus 0.215, and that is 0.785. So area to the left of this positive Z value, that is 0.785. We convert it to this form. We say probability of Z less than that positive value, that is 0.785. Now, this is something that is in the standard form. Go to the table, find the Z value corresponding to this. That turns out to be 0.789 from the table. Now, the actual Z value was supposed to be positive, as we found earlier. So we put a negative sign with this, minus 0.789, and then just input in the formula, find the value of B from that, and that gives you the result. Okay, so that's how inverse normal works. These are the 4 standard cases that you would have here for one-sided intervals. For two-sided intervals, it's a bit more complicated. That's very rare as well, but we will see that when we do some questions. I have a couple of examples lined up in which you have two-sided intervals, which we'll talk about them. So that's the second major part of normal distribution that we have. Inverse normal, when you have probability given and you have to find some missing information from the data. Then the third major concept that you have here is binomial to normal approximation. Now, let's think about this. You've got this example. It says, assume that for a randomly chosen person, the next birthday is equally likely to occur on any day of the week. That means every day has equal probability what's the probability of the birthday being on a Monday? That's 1/7, right? And for every day, it's 1/7. Now, they want us to find that out of 350 randomly chosen people, at least 47 will have their next birthday on a Monday. Now, what kind of distribution is that? We have some repetition going on. We've got 350 people that we're talking about. For each of them, the probability that the birthday is on Monday is the same, right? For every person, it's the same probability. That's 1/7. So we could say it's a binomial distribution because n is 350. Probability of success 1/7. If you call this a success, having your birthday on a Monday, then probability of failure would be 6/7. So what we're actually looking for now is probability that you have at least 47 successes, So that becomes x greater than or equal to 47. That's what you have to find in binomial distribution. Now, x greater than or equal to 47, what does that mean? The total number was 350. You have to find all the probabilities from 47 onward. 47, 48, 49, 50, 51, 52, all the way up to 350. That's a lot of probabilities to calculate. How do you do that? That's very complicated, right? That's going to be a lot of calculation. Even if you do the other way around, if you do, okay, if you say that these probabilities are too much to calculate, what if you do 1 minus probability of x less than 47? Can you do it that way? In that case as well, you have to find probabilities for x equals 0, 1, 2, 3, 4, all the way up to 46 and subtract all of them from 1. Again, too much calculation. It's not feasible to do it manually. So in such cases, what we do is we use something that we call binomial to normal approximation, which the calculation from binomial directly becomes very tedious. It becomes very long. Okay. Now, how is that done? How do you convert it to a normal distribution? If it was a binomial distribution, these were the values of n, p, and q that we had there. In normal distribution, the parameters are mean and standard deviation. Right? These are the parameters of a normal distribution, mu and sigma. How do you find mean and sigma from this? For a binomial distribution, remember mean is given by n times p. Standard deviation is square root of npq. In the formula sheet, you have the variance given, that's npq. Standard deviation will just be the square root of that. That's square root of npq. You find the corresponding mean value and the standard deviation value from this. Once we have these values, we can now think of it as a normal distribution and find the probability from that. But there's another problem here, and that problem is we've got this as a discrete distribution. So greater than or equal to 47, what that means is, in discrete distribution, greater than or equal to 47 actually means if you have this number 47, and this is 48, this is 49, then greater than or equal to 47 means that 47 is supposed to be considered, 48 is supposed to be considered, 49 is supposed to be considered, and 46, 45, they're not going to be considered. So these values, we will consider all of them, the values to the right of 47, and these values, we're not going to consider values to the left of 46. And for discrete distributions, that's perfectly okay. There's no problem with that. Because the decimal value, there are no decimal values that can exist here, right? So we just consider the region to the right of 47, the region to the left of 46. But the problem in normal distribution is when we convert it to normal distribution is a continuous distribution. So in a continuous distribution, values can also be in decimal. So we can also have some value in the middle here. We can have 46.1, 46.2, 46.5, 46.7. What do we do with those values? In discrete, that was not a problem because greater than or equal to 47 meant that we have to select these and not select these. Now, in normal distribution, what do we do with this region in the middle? What we do is we say, let's divide it into half. So the problem is, do we consider this region or do we not consider this region? So on that normal distribution curve, the region between 46 and 47, will we count that in this probability or will we not count that? Right? That's the problem. So what we say is, let's break it in two halves, break it in the middle, 46.5. So any value that's less than 46.5, that will round off to 46. Any value that's greater than 46.5, that will round up to 47. So we have the cutoff point in normal distribution 46.5, and we say, if you have x greater than or equal to 47 here, in normal distribution, we would say that becomes greater than 46.5. Now, I'll tell you exactly using some examples how to do this in different cases. But the idea is you convert it like this. First of all, once you've converted to this form, then the next thing is just finding the z value from that and finding the probability from the table. That's something that we have done already. Once you've converted it to normal like this, find the z value from this. That will give you something like this, and then you convert it to the standard form, z less than positive, using the methods that we've discussed earlier. Find the probability from the table, and you get that result. Now, how exactly do you do this? This is called continuity correction. What we're doing here. Let's do some examples of that. So one thing that you have to do is you have to find the mean of this distribution and the standard deviation. These are two things that you have to do. But then, how do you do this continuity correction? Let's do that in a bit more detail. Consider that same example, greater than or equal to 47. Now you get the idea, why do we need to do that? But now what's the process that you would follow to figure out what number we are going to have here? For example, if you have x greater than or equal to 47, if you have something like this, what you would do would be, you would consider three numbers. One, that same number, 47, one number bigger than that, one number smaller than that. So 46, 47, 48. And you think about these numbers, is 46 going to be included in this greater than or equal to 47? Does that satisfy this condition? No, 46 does not satisfy the condition. Does 47 satisfy the condition? Yes. 48, yes. Now, wherever the decision is changing, included and not included, between cross and tick, this is where you break. This is where you split these numbers and you say, okay, in normal distribution, we would say we consider the midpoint of this, 46 and 47. So in normal, it will become greater than 46.5. The midpoint of those two numbers, that's 46.5. Now in normal distribution, it doesn't matter if you put the equal to sign there or not, or don't do that. We talked about that in the beginning. So that does not matter, but we choose the midpoint here of 46 and 47. So it becomes 46.5. If you had this, x greater than 47, what would you do in this case? Again, you think of those three numbers. Is 46 included? No. 47? No. 48? Yes. So it's changing between 47 and 48. You use the midpoint of them. That's 47.5. So in normal distribution, it will become greater than 47.5. That'll be the probability that you find from the table after converting it to z. If you had x less than 93, again, you think of these three numbers. One number less than that, one number greater than that, and one number itself. 92, is that included? Yes. 93, is that included? No. 94, no. So between tick and cross, you've got 92.5. You say this is x less than 92.5. And then finally, if you have x less than or equal to 145, again, you think of those three numbers. 144, is that included? Yes. 145, yes. 146, no. Decision changes between 45 and 46. So you choose the midpoint of them. 145.5. That's what you do in normal distribution after continuity correction. Okay, so that's how you would be converting something to normal distribution. Sometimes you have to figure it out yourself. So in this question, for example, calculating these probabilities, there were so many calculations, like 47, 48, 49. There were too much calculation that was not feasible to do it manually. So we converted it to normal distribution for that reason. Mostly they will tell you in the question. Mostly they will tell you in the question that you have to use this approximation. So whenever they say in a question, use an approximation, use a suitable approximation, there's only one type of approximation that you have in your syllabus, and that is binomial to normal approximation. So the word approximation in the question, that would tell you that the original distribution is binomial and you have to convert it to normal. And that's one of the easier questions that you would find on both binomial and normal distribution. Okay, so you convert it to mean, you find the mean standard deviation for normal, do continuity correction, and find that probability. But there's some conditions. You cannot use this approximation every single time. There's some condition for this, and that condition is that the data should be large enough. Now, the criteria that we use for data being large is this. You need to memorize these conditions. N times P should be greater than 5, and N times Q should be greater than 5. N is the total number of values in binomial distribution, total number of repetitions. P is the probability of success, Q is the probability of failure. For a normal distribution, for an approximation from binomial to normal to be reliable, both of these conditions have to be satisfied. Both of these conditions have to be satisfied. If any of them is not satisfied, then we cannot use approximation. That is the result that we get from that is not going to be a good estimate. It's not going to be reliable. For example, in this case, n was 350. Probability of success was 1/7. So n times p is 50. 50 is greater than 5. That satisfies the condition. N times q, that is 300. 300 is greater than 5. That satisfies the condition. Both conditions are satisfied here. So in this case, it is appropriate to use this approximation. If any of these numbers was less than 5, it would not be appropriate. Okay, so that's the cutoff point that we use in our syllabus to figure out if this approximation is valid or appropriate or not. Okay, all right. For example, this is one case. You have to use a normal approximation to find the probability of this. You can have a look at this example. You have P, N, P, and Q. You have to find X less than 25. Do continuity correction. Find the mean and standard deviation. Find that probability. You get that result. Right? That's pretty straightforward. Now, in the second part, they say give a reason why the use of normal approximation is justified. You would have to find these two values. You would find N times P. N times P turns out to be 24. That is greater than 5. N times Q, that turns out to be 6. 6 is greater than 5. Both of these conditions are met. Since both of these conditions are met, that justifies the use of normal approximation. If any of those numbers was not greater than 5, we would not be able to use this approximation. The greater these numbers are, the better your approximation is going to be. If these numbers are smaller, then the approximation is not going to be as good. But that's the cutoff that we will be using. If they're equal to 5, the condition is greater than 5. So you will not get a question in which it's equal to 5. But according to this criteria that we use in Cambridge, if it's exactly equal to 5, we will not do that. It has to be greater than 5. Okay. Greater than 5 is the condition. Okay, let's have a look at some examples now. A few simpler ones, and then we'll look at the more difficult ones. Let's say we've got daily minimum temperatures in degrees in a particular city, and we've got the normal distribution such that the mean of that distribution is minus 15.1, and the standard deviation, the variance is 62. Standard deviation would be square root of 62. We have to find the probability that a randomly chosen day in January in Ottawa has a minimum temperature above 0 degrees Celsius. So what's the probability of the temperature being above 0 degrees Celsius? That means probability of X greater than 0. That's what you have to figure out. How do you do that? You first of all convert it to Z using this formula. Z is X minus mu over sigma. So it becomes Z greater than this using the formula. Right? You get Z greater than 1.918. Again, you think of the normal distribution curve. This is not the standard form. You do 1 minus the area to the left of this to convert it to standard form. Find this from the table and you get the result. Right? So sometimes you have very simple problems like this. You have one part of normal distribution question that is fairly straightforward, simple normal distribution. You have the data given, you have to find the probability from that. The next part is inverse normal. That's going to be generally the more complicated part. In this case, that's also straightforward, but sometimes this is the more complicated part. Let's have a look at this. In another city, the temperature is a random variable with this distribution. Mean mu, variance 40. Do not say that standard deviation is 40. That's a very common error. This number represents variance. Okay, so standard deviation would be square root of that. We are given that the probability of the temperature being above 0 is 0.888 in this case. Find the value of mean. How do we think about this? We say probability of X greater than 0 is this. Convert that to Z. Z greater than some value is negative. Some value is 0.888. Figure out whether Z is negative or positive. We know that area to the right here is supposed to be bigger. If the area to the right is bigger, that means Z is supposed to be a negative value. So this area is 0.888. You flip that. When you flip that, you can say the area to the left of the positive Z value, that's also going to be 0.888. Find that value from the table. Make that negative because it was supposed to be a negative value. Put that in the formula and you get the result from that. Okay, so that's a relatively simple problem that you see on inverse normal. Let's have a look at another example. Okay, so just a minute. My pencil is running out of battery. I will just resume in 1 minute. Okay, since that charges a little, then we resume. No, it's I think first generation. It's not Pro. It's the one before that. It's been some time. I think it's 3 years old now. So its battery is not very good. But it did not get charged at night. I forgot to put it on charging, so that's why I think it just ran out of battery. That happens sometimes. Okay, let's resume. Okay, so sometimes they ask you to give examples like this of a normal distribution variable. Remember, normal distribution is used for any continuous variable. So any variable that you can think of that can take any decimal value. You can use that, for example, height, weight, temperature, mass, length, anything that can take any decimal value. Okay. So you can write any of them, any one of them. These are just, multiple examples. You can choose any of them. The second part is inverse normal. We will skip that. That's standard part. Now, sometimes they want you to find expected value of something. For example, they're saying if 300 observations are taken at random from the distribution in part 2, in this part 2, estimate how many of these would be greater than 22. Now, how do you approach these problems? You would find the probability of one observation being greater than 22, first of all. Find the probability of one observation being greater than 22. So you'll find that using simple normal distribution, probability of x greater than 22, convert that to z, find that probability. That's the probability of one observation being greater than 22. But then, how many out of 300 observations would you expect to be greater than 22? This is the probability of one being greater than 22. You multiply this by the number of observations. That's 300, 300 into that. This is what you would expect. This is turning out to be a decimal value. When you talk about number of observations, that has to be an integer. So you round this off. This rounds off to 7. You would write 7 as the final result. Always round it off to an integer. Decimal value is not going to be acceptable when they talk about number of something. It has to be an integer at the end. The answer has to be an integer, otherwise we'll lose 1 mark. Okay, so when they ask you to find expected value of something or estimate how many times out of a certain number you would expect something to be true, you find the probability for 1 and then you multiply that by that number to get that expected number. Okay, now sometimes they ask you to find probabilities and they don't give you numbers, but they ask you to do it in terms of mu and sigma like this. Now, don't get scared by that, because when you start working, when you start inputting values in the formula, you will figure out that these unknowns will start canceling out. For example, they have told us that a distribution has mean mu and standard deviation sigma. Now, then they've not given us any numbers here. And they're saying, how many of them would you expect? So if 800 observations are taken, how many would you expect to be between mu minus sigma and mu plus sigma? Let's first of all find the probability for one observation being between this interval, being within this interval. For one observation, you can say probability of x between mu minus sigma and mu plus sigma. Okay, that's what we're looking for. Now use the formula z is equal to x minus mu over sigma to convert it to z. When you convert it to z, you see what happens. Mu and mu get cancelled, and then the sigma and sigma, they also get cancelled. And you get z between -1 and 1. That's the final result that you get from this. Now, these are numbers, z between -1 and 1. You can find that if it's between -1 and 1, one way of doing this could be, you can say on the normal distribution curve, this is -1, this is +1. Since the curve is symmetric, whatever is the area on the left side of the mean in this case, since both of these numbers are the same, right, in terms of their magnitude, they're the same distance away from 0. Whatever is the area on this side, that's going to be the same as the area on this side. So you can find any one of those areas and multiply that by 2. So what I've done here is I've said probability of z being between -1 and 1. That's the same thing as saying 2 times probability of z between 0 and 1. How do you find between 0 and 1? Find the area to the left of 1, this area, subtract from that this area, that's the 0.5, right? Area to the left of the mean, and that will give you the result. You find, use the table for this, that's 0.8413, and then just input that, you get the result, that's 0.6826. That's the probability. And then what's the expected value then? For the expected value, what you would do would be, you would multiply this by 800. You would say 800 times 0.6826, and you would get some value from that. That will be in decimals. You have to write an integer value for that. Okay, write an integer value, and that will be your final result. Okay, so if you have something like this, don't just leave it as it is, as in don't think it's very difficult. Just input in the formula and things will start canceling out themselves. Okay, all right, let's move on. We've talked about this already. It's a repetition. Okay, there's a variable x, and we're given that it follows normally distributed, follows normal distribution with mean mu and variance sigma square. It's given that probability of x greater than 30 is equal to this. Probability of x greater than 20.9, that is equal to 0.6228. So you're given two separate pieces of information, and you want to find the value for mean and standard deviation. Mu and sigma, that's what we're looking for. We're looking for mean and sigma, right? Okay, so there's something wrong with OneNote. Okay, so we were here. So now in this case, they say the random variable x is the length of time that this person takes to mend a bicycle puncture. X follows normal distribution with mean mu and variance this, and they've given us two pieces of information. Probability that x is greater than 30, that is equal to 0.1480, and the probability that x is greater than 20.9, that is equal to 0.6228. Now, we've got probability values given for both of them. We have to find mu and sigma. So this is inverse normal, right? Probability is given, and we have to find mean and sigma. Now, these are two separate equations that were given. What we do is we apply the inverse normal method on both of them separately, on this separately, on this separately. We get two equations from them. One this equation and not this equation. And then we solve those two equations simultaneously, right? Solve this and this simultaneously, and that will give you the value for mean and sigma. So that's something that can also happen sometimes, that they give you two pieces of information, you make two equations from them, and then you solve them simultaneously to get the result, right? For each of them, it's the standard inverse normal problem. You make two equations from them, and then you solve them simultaneously. Okay, so that's something that could also happen sometimes. Okay, let's have a look at this example. The time spent, let's call that X, by people visiting a certain dentist are independent and normally distributed. So we've got normal distribution here again. The mean of this distribution is 8.2. 79% of people who visit this dentist have visits lasting less than 10 minutes. So we are given the probability that a visit lasting less than 10 minutes, the probability of that is 0.79, right? 79% is 0.79. Find the standard deviation of the time spent by people visiting this dentist. We've got the mean given, and we have to find the standard deviation. That's what we're looking for. Okay, so this is standard inverse normal problem. Convert it to Z, figure out whether Z value is positive or negative, convert it to standard form, use the table, put that in the formula, you get the value that we were looking for. Now, second part is what I want to focus on. It says, find the probability that the time spent visiting this dentist deviates from the mean by more than 1 minute. How do you understand that? Deviates from the mean by more than 1 minute. Now, what's the mean? Mean is 8.2. Mean is 8.2. If it deviates from the mean by more than 1 minute, what that means is, if you've got 8.2 here in the middle, 1 minute on this side is going to take us to 9.2. 1 minute on the other side is going to take us to 7.2. It deviates more than 1 minute. So that means we are either in this region to the left of 7.2 or in this region to the right of 9.2. These are two regions that we have that satisfy that condition. So we say the probability that we're looking for is probability of X being less than 7.2 and the probability of X being greater than 9.2. We have to find these two probabilities, and that's going to give us the result. Okay, so something happened to this normal distribution curve that I had here, but it would look like this. So this is the normal distribution curve. This is what it would look like. What you're looking for is, you've got Z value on the left side somewhere. This is minus 0.448. You've got Z value on the right side, 0.448. You're looking for these two regions and you have to add them up together. Area to the left side here, area to this side here, and area to the right side here. You're looking for both of these regions. So you convert it to Z value. That gives you this and this. Now, if you think about it, these are both the same, right? Because the curve is symmetric, this area and this area, they're both the same. So we can just try and find one of them. Finding it for the positive value, it's easier. You just do that calculation, and then you say the other one is also going to be the same because of the symmetry of the curve, and that gives you the final probability. Okay. So deviate by more than 1 minute. In this case, what does that mean? To the right of 9.2 and to the left of 7.2. Okay. All right. Then it says, find the probability that of 6 randomly chosen people, more than 2 have visits lasting longer than 10 minutes. Now, this is where they have two distributions. Remember, in binomial distribution, we talked about when you have two binomial distributions, one binomial inside another binomial. In normal distribution, that can happen as well, that you have one binomial distribution. And to find the probability of success for that, you have to use a normal distribution. So look at this example. 6 randomly chosen people, more than 2 have visits lasting more than 10 minutes. Now we're talking about people. That's a discrete variable, number of people, right? That's discrete. So that cannot be normal distribution. This is binomial distribution with n being equal to 6. And the criteria for success is that the visit lasts longer than 10 minutes. So this is a binomial distribution where this is the criteria for success. Now, what's the probability for success? They've given that in the question. 79% have visits lasting less than 10 minutes. This is longer than 10 minutes. If less than 10 minutes is 0.79, longer than 10 minutes would be 1 minus 0.79, that's 0.21. This is the probability for success. So this is a binomial distribution now with n equal to 6, probability of success 0.21, failure 0.79. Find the probability that x is greater than 2, more than 2 successes, and that will give you the result using binomial distribution. Okay. Then it says find the probability that of 35 randomly chosen people, fewer than 16 have visits lasting less than 8.2 minutes. Again, how do you think about this? 35 randomly chosen people, 35 people. That's a discrete variable, right? A number of people. Fewer than 16 have visits lasting less than 8.2 minutes. N is 35. This is the criteria for success. Visit lasts less than 8.2 minutes. How do you find the probability of this? Visit lasts less than 8.2 minutes. You have to use normal distribution for that. Now, in this case, it's easier because you knew that the mean is 8.2. If the mean is 8.2, then less than 8.2 probability of that would just be 0.5 in this case. But if it was some other number, we would first have to find that probability using normal distribution, and that would become the probability of success for this binomial. So it looks like this. It's a binomial distribution with n35, probability of success 0.5, probability of failure 0.5. Okay. And now what you're looking for is probability of having less than 16 successes, less than 16 successes. That's what they want, right? Fewer than 16 successes, less than 16 successes. Now, what does that mean? Now, you see in the question, they have not talked about any approximation or anything, but you know that this is binomial distribution and you have to find probability of x less than 16. Now, how do you do that? Less than 16 means x equals 0, 1, 2, 3, 4, 5, 6, all the way up to 15. That's a lot of calculation. On the other hand, if you do 1 minus the remaining probabilities, that will also be too much. 16, 17, 18, all the way up to 35. That's too much calculation if you try to do it directly. So you have to figure it out yourself that you have to use normal approximation here. Convert it to normal distribution, find the mean standard deviation, do continuity correction, and solve it as a normal distribution. And that gives you the result. You can check that the conditions are satisfied. NP and NQ. NP, you can see that's greater than 5. NQ is greater than 5. Both of those conditions are met. So you can use approximation. So that's what you do here. Okay. It says visits lasting less than 8.2 minutes. This has to be found from the normal distribution, right? Now, if it was any other number, for example, if it was x less than 8.9, for instance, we would have to use normal distribution first of all, because times were normally distributed to find that probability. But in this case, they've made it easier. They've said x less than 8.2. 8.2 is the mean value. We know the curve is symmetric. So if it's 8.2, then to the left of 8.2, the area is 0.5, right? To the left of the mean is 0.5, to the right of mean is 0.5. So the probability of success directly comes out to be 0.5 in this case, because we're talking about area on one side of the mean. If it was anything else apart from 8.2, we would have had to do that calculation ourselves, first of all, using normal distribution. Okay, so that's one of the more complicated problems in which you have a binomial distribution, and to find the probability of success for that, you have to use normal distribution. Okay, let's have a look at this example. There's a normal distribution with mean 20 grams, and 94% of the letters have weights within 12 grams of the mean. Okay, now how do you understand that? Mean is 20. 94% have means that have weights that are within 12 grams. 20 is the mean. Within 12 grams of the mean, you go 12 to the left, 12 to the right. It's between 8 and 32. Between 8 and 32. We are given probability of x being between 8 and 32. That is equal to 0.94. That's equal to 0.94. That's what we're given. Now this is inverse normal. Yeah, this is inverse normal. We have to find the standard deviation. Probability is given, we have to find standard deviation. Now, how do we do this? think of the normal distribution curve. You can convert it to Z first of all if you want, and then think of the normal distribution curve, or think of the curve first and then convert that to Z. Both of them are okay. In this case, I've done it directly. 20 is in the middle, right? 8 is on the right, on the left side, 32 is on the right side. Now think about it. We are talking about area between these two values to be 0.94. Now the problem is in inverse normal, we did not cover what happens when you have an interval like this, two-sided interval. This is something that you have to figure out based on the question because it varies across questions. Now in this case, you have to somehow convert it to a single interval, single-sided interval. This is a two-sided interval between 8 and 32. You have to somehow convert it to single-sided intervals to be able to apply inverse normal. Now, how would you do that? Look at this curve. Between 8 and 32, the area is 0.94. Now, remember the curve is symmetric. The curve is symmetric. And both of these numbers are equal distance from the mean on both sides. If the area in the middle is 0.94, what's the area that's left? 0.06, 1 minus 0.94. That's the remaining area. That remaining area is divided equally on both sides. 0.03 on the left side, 0.03 on the right side. So we can say if the area between 8 and 32 is 0.94, then the total area to the left of 32, can we say anything about that? The total area to the left of 32, that is 0.94 plus 0.03. That is 0.97. So we could convert it to a single-sided interval like this. X less than 32, that probability is 0.97. And then it becomes a simple, that becomes a standard inverse normal problem from here onwards. You convert it to Z, write this in terms of Z, figure out whether Z is positive or negative, find the value of Z from the table, and put that in the formula, and you get that value for standard deviation. So if you have two-sided intervals in inverse normal like this, you have to somehow figure out a way to convert them to one-sided intervals. So that's what you could do in this case using the symmetry of the curve. We could say area to the left of 32, that is 0.97. And then we just do it afterwards, like normally do. Find the probability that a letter weighs more than 13 grams. That's simple, normal. That's fairly straightforward. You can look at this working. In the last part, it says find the probability that at least 2 of a random sample of 7 letters, at least 2 of a random sample of 7 letters have weights which are more than 12 grams above the mean. Now, how do you understand that? First of all, this is binomial, right? Because we're talking about a sample of 7 letters, number of letters, and we want at least 2 successes, That's binomial distribution. What's the criteria for success here? A letter having more than 12 grams, a letter having weight more than 12 grams above the mean. This is the criteria for success. Now, first of all, we can find the probability for success. More than 12 grams above the mean. How do you understand that? Mean is 20. Standard deviation is 0.38. In fact, we don't need to do any calculations here. If you think about it, we are given that information. Yeah, so we're given that information. We use that in the first part as well. More than 12 grams above the mean, what does that mean? More than 32. Probability of X being greater than 32. Now, using the symmetry of the curve in the first part already, we know area to the right of 32, how much is that? That's 0.03. Okay. If we did not know that, we would have to do that calculation using normal distribution, first of all, to find that probability. But we've done that work already using symmetry. We know that that area on the right side of 32, that is 0.03. So that's your criteria for success. Probability of success is 0.03, therefore. Failure, 0.97. And 7, find the probability of having equal to or more than 2 successes. Greater than or equal to 2 successes. Find that like you normally do. You reverse that because 2 to 7 is more probabilities as compared to just 0, 1. Subtract from 1 probability of x equals 0 and probability of x equals 1, and you get the result from that. Okay, so sometimes you can have binomial distribution, and the probability of success of that is found using normal distribution like this. Okay, just a few more examples. No, yeah, just a couple more, I think. Let's have a look at the next one now. Okay. The time x hours for which students use a games machine on any given day is normally distributed with this mean and standard deviation. On how many days of the year would you expect a randomly chosen student to use the game machine for less than 4 hours? Find the probability for one student that he uses it for less than 4 hours, and then multiply that by 365. Okay, so for one student, it's this. Using simple normal distribution, multiply that by 365, you get this. And then you round that off to an integer. Rounding that off is necessary, and that will give you the result. Second part is just inverse normal. Probability of x greater than k is 0.2. And you can just, find the value of k using inverse normal, right? We have done that multiple times. The last part is what I want to focus on in this. The last part says, find the number of hours for which a randomly chosen student uses the games machine in a day that is within 1.5 standard deviations of the mean. Within 1.5 standard deviations of the mean. Now, how do you think about this? One idea is that you think of it like this, that you say, okay, x is 3.24. 1.5 times the standard deviation, you find that. And you have to be between 1.5 times 0.96 plus this and 3.24 minus 1.5 times 0.96. X is going to be between these two values. Within 1.5 standard deviation, what does that mean? It could be 1.5 standard deviations above the mean or below the mean. So it has to be between these two values. Okay, between these two values. So you could do something like this. That's one idea. You say x is between 3.24 minus this or plus this, and that turns out to be this. And then you solve that like you normally do. However, there's a much more efficient way of doing this, and that is using that understanding of z that I told you about earlier. Z value represents the number of standard deviations you are away from the mean. Remember we talked about that in the very beginning. Z represents the number of standard deviations that you're above or below the mean. So when they talk about something like this, that a variable is within 1.5 standard deviations of the mean, what does that mean? If we think of the Z distribution directly, we can directly think about the Z. The mean of Z is 0. Within 1.5 standard deviations means minus 1.5 on the left side and 1.5 on the right side. In a Z distribution, standard deviation is 1, right? So for a Z distribution directly, we could say Z has to be between minus 1.5 and plus 1.5. Do not even think about X. Just directly use the Z value like this. You would say Z is between minus 1.5 and plus 1.5. Okay. You can skip all of this work where you write that in terms of X first of all, then convert it to Z. That's not required because we know already in terms of Z, we can write it like this. Find this probability. How do you do that? Using the methods that were done earlier, you can look at this working. That's how it would work. Okay, let's take this example. Again, the first part is pretty straightforward. The second part asks you to do something very similar. You've got mean times, and you've got times taken by students to get up in the morning. They have normal distribution this and standard deviation this. Okay. The second part says very slow students are students whose time to get up is more than 1.645 standard deviations above the mean. What do you understand from that? More than 1.645 above the mean. Now, this is the mean, 26.4. So you'll say 26.4 plus 1.645 times 3.7, which is the standard deviation. X has to be greater than this. Okay. But a direct way of doing that is when they talk about standard deviations that you're away from the mean, you could do it directly like this. You could say more than 1.645 above the mean That's the same thing as saying probability of Z is greater than 1.645 directly. You do not even have to do this calculation. You can directly write Z greater than 1.645. Just directly write this. And then you find that probability. You see what that turns out to be. They're saying find the probability that fewer than 3 students from a random sample of 8 are very slow. That's binomial distribution now. N is 8. Success is being very slow, right? That's your ideal world in which being very slow is successful. So a random sample of 8 students, out of them, what's the probability of having less than 3 successes? You find the probability for being very slow, first of all. You would say that is probability of Z greater than 1.645. Find this from the normal distribution curve. And then you just use binomial distribution to find that probability that you had less than 3 successes with N equal to 8, P equal to 0.05 from there from the normal distribution, and Q equal to 0.95. The probability of success is coming from normal distribution in this case. Okay, let's have a look at another example. Again, inverse normal in which you have two-sided interval. You've got tire pressures of a certain type of car. They follow normal distribution. Mean is 1.9, standard deviation 0.15. We've got the mean and standard deviation given. Find the probability that all 4 tires on a car of this type have pressures between 1.82 and 1.92. Now, for one tire, can we find that? We can find this probability for one car. For one tire, find this probability X between 1.82 and 1.92. Do it using the normal method. Convert it to Z first of all. Find this probability. And that probability turns out to be 0.2558, right? It's that case in which one Z value is negative, the other is positive. We've discussed that before. You find this probability. Now they're saying probability that all four tires satisfy this condition. So this is the probability for one of them. For all 4, what we can do is we can just multiply this by itself 4 times, 0.2558 into 0.2558 into 0.258 4 times. So that becomes this power 4, and that gives you the required probability. In the second part, it says, safety regulations state that the pressures must be between 1.9 minus B and 1.9 plus B. It's known that 80% of the tires are within these safe limits. So you're given the probability. You need to find these safety limits. So you need to find the value for B here. And then you can write down the safety limits as well. So what do we know? Probability of X being between these two values. This is 0.8. 80%, that's 0.8. And we have to find the value for B somehow. This is inverse normal. We've got the mean, we've got the standard deviation, but this value is missing. We don't know what the value for B is. How do we think about this? What was the mean? Mean was 1.9 here. Mean was 1.9, right? So 1.9 minus B and 1.9 plus B, what does that mean? We got 1.9 exactly in the middle. You got 1.9 in the middle. Plus B means you go B units to the right. Minus B means you go B units to the left. Now, since the curve is symmetric, we know, first of all, they've given that this area in the middle is 0.8. If this area is 0.8, what's the remaining area? That's 0.2. That's going to be equally divided on both sides. 0.1 on the left side, 0.1 on the right side. So now we can convert it to a one-sided interval. We can say, if the middle region is 0.8, then the region on the left side of this value, 1.9 plus B, what's that total region? That total region is 0.1 plus 0.8, and that's 0.9. So we can convert it to a one-sided interval like this. Probability of X less than 1.9 plus B, that is equal to 0.9. And then you convert it to Z. Write this in terms of Z. Figure out whether Z is positive or negative. Use the standard inverse normal method. Find the value of B from that. Once you have the value for B, you can write down the safety limits, 1.9 minus that and 1.9 plus that. And that gives you that safety limit. Okay, so when you have two-sided interval, in case of inverse normal, you have to find a way using the normal distribution curve to first of all convert that to a one-sided interval, and then you can just use that method for finding the method for inverse normal that we normally use. Okay, let's have a look at this now. So in this city, the heights are normally distributed with mean 176 and standard deviation 4.8. Find the probability that an adult has a height greater than 170. That's fairly straightforward. Let's look at the second part of this. In the second part, it says 60% have height between 170 and K. 60% of adults have heights between 170 and K. So what are we given? We're given probability of X being between 170 and K, that is equal to 0.6. That's what we're given. Probability of X being between 170 and K, that is 0.6. Where K is greater than 70, so it has to be some value greater than 70. Find the value for K, giving an answer greater to 1 decimal place. How do you think about this? Again, this is inverse normal. We have a two-sided interval. We can't work with two-sided intervals in inverse normal. We have to convert it to a simple normal. Okay. Now, how do we think about this? So we've got one value. So if we convert it to standard normal, you can do it directly or convert it to standard normal first of all. So in this case, what I've done is I've converted it to Z first of all. 170 minus the mean was 176, standard deviation was 4.8. That gives me that Z is between minus 1.25 and this value. Okay. Now you could do it in terms of X first and then convert it to this. Both are fine. In the previous examples, I did that directly. In this case, I've converted it to Z first of all. Both are fine. They will work every time. So between 170 and K, or between these two values of Z, we know that the area is 0.6. Now, first of all, we need to figure out whether this value, the other value, if that's positive or negative. That is going to be positive because we've got one negative value and the area between them is what? 0.6. If the area is 0.6, on the left side, the total area is only 0.5. So if it's 0.6, the other value has to be on the other side. It has to be on the positive side. So that's what we know for sure. Okay. Now the problem is, we only know that this region, this yellow region is 0.6. That's what we are given. Okay, that's what we're given. How do you find the value for K? We know that this area is 0.6. Can we find the area to the left of minus 1.25 somehow? The area to the left of minus 1.25? We found that in the previous part of this question. In the previous part of the question, we found the probability corresponding to the Z value of 1.25. 1.25 on the left side of that, we found in the first part, this area was 0.8944. If that's 0.8944, what I've done is, I've said, this small region here, that would be 1 minus that, and that's 0.106. So it's 1056. This area is 0.1056. So here now, in this case, you could say this area is 0.1056. If this is 0.1056, then what's the total area to the left of the Z value? What's this total area? This total area is this plus 0.6, and that will give you 0.7056. And now what you can do is you can find the probability value corresponding to 0.7056, and that will give you that Z value. And you can find the Z value from the table. Once you have that, you input that in the formula. X minus mu over sigma equals Z. And that gives you that result, which turns out to be 178.6. So sometimes it can be something as complicated as this as well. Okay, you can have a look at this solution in your own time. This is pretty complicated. I think one of the most difficult questions that you find in normal distribution, because of it being an inverse normal problem, two-sided interval, converting it to one-sided interval is fairly complicated in this case. One last example. This is something that you'll see a lot in recent papers, problems like these. A farmer sells eggs. The weights in grams of these eggs can be modeled by a normal distribution with mean 80.5 and standard deviation 6.6. Eggs can be classified as small, medium, and large based on their weight. A small egg weighs less than 76 grams, and 40% of the eggs are classified as medium. Find the percentage of eggs that are classified as small. Now, the first part is pretty straightforward. We are given that a small egg is that weighs less than 76. Just find the probability for that. Now, the second part says, find the least possible weight of an egg classified as large. Now, in the first part, what we have found is that 24.76% of the eggs are small. So this is 24.76%. They have told us in the question that 40% are medium. So these are 40%. So from that, we can figure out how many are large. 100% minus these other values, that will give you the probability of an egg being large. And that turns out to be 35.24%. Now, you know the mean of this distribution. Mean is given to be 80.5, standard deviation is 6.6. You need to find that number. So it's like this, basically. You've got 3 types of eggs, small, medium, and large. There'll be some value here. That's the cutoff point for small, and they've given us that this cutoff is 76. This point we do not know. Let's call this point A. To the right of A, we know that this probability is what? 0.3524. So we write it like this. Probability of eggs being greater than A, that is 0.3524. That's the least possible weight of a large egg. We have to find the value for A. So we can think of it like this. This is an inverse normal problem now. Find the value of A from that. And that's the cutoff point for an egg being classified as large. Okay. So that's all a normal distribution. So there are 3 different cases that you would see. Number 1, you'll have the data given, and you have to find the probability. You'll have x, mu, and sigma given. You'll have to find probability. How do you do that? Convert x to z using x minus mu or sigma. Convert that to standard form, z less than a positive value, and then you use the table to find that probability. The second possibility is inverse normal. You have the probability given. You write that probability in terms of z first of all, and you have to find missing information from the data, right? So something might be missing from this. You write that probability in terms of z first of all, figure out whether z is positive or negative, convert that to this standard form, and then use the table to find the value of z corresponding to that probability value, assign the appropriate plus minus sign to that, and then use the formula to find any unknowns that we have. And then finally, we did binomial to normal approximation. We'll have NPQ, convert them to mu and sigma using the formulas, do continuity correction, and then find the probability using normal distribution. These are the conditions. NP should be greater than 5 and NQ should be greater than 5. And then we looked at a number of examples on this. I hope that makes sense. If you have any questions, you can let me know now.